questions from last time? So let me remind you where we were yesterday. So I was working on a bound for the number of primes in an interval from x to x plus y. And we bounded this by counting the number of n from x to x plus y, all of whose prime factors are bigger than some number r. And then we bounded this quantity by Selberg's idea, making use of the fact that squares are positive. We reduced this to the problem of minimizing a quadratic form while keeping a linear form fixed. And we arrived yesterday at the following bound, y divided by, maybe you can remind me if I get something wrong. So y divided by L plus, so L was going to be something like the sum over, what did we have? R less than Z. P divides R implies P bigger than R, less than R. Right? Supported only on numbers all of whose prime factors are less than this number capital R. And then something like mu of R squared divided by phi of R. Right? And then there was a remainder term that we worked out explicitly last time as well, which was something like 1 over L squared, and then a sum over n less than z, again, supported only on right? And then here I had something like mu of n squared sigma of n divided by phi of n. And this quantity squared. Is this good? Okay. Any questions on this? Okay. So let's discuss a little bit what these quantities mean, what the size of L is, and what bound we've actually proved using all of this, right? Now, okay, so maybe you discussed, so yesterday I think in one of the discussion sessions, you discussed things like, well, you know, phi of n is usually at least as large as something like, well, it's always larger than n over log n, something like that. Is that right? Yeah? But usually the size of phi of n is really on the scale of n, right? This 1 over log n comes up only in the very rare case when n happens to be like a primorial, the product of the first few primes. Otherwise, we should be able to do better. So, but usually, phi of n is on the scale of n. Okay? So, and again, in the same way, however you prove this, you can also prove that sigma of n is no more than n times log n. Right? So again, if you chose a primorial, if you chose something badly, then sigma of n could be a little bit larger than n, and phi of n could be a little bit smaller than n, right? And the ratio could be a little bit larger than 1. But usually, again, sigma of n is also going to be of the same size as n. Okay? So if you believe these two facts, then what you should think of is that this sigma of n over phi of n is usually of size 1. Right? Although its maximal size could be like log n squared, but that happens extremely rarely. Okay? So now, using this, you might expect that if I just count the sum over n up to z, some object like mu of n squared, sigma of n over phi of n, which looks like a kind of a messy thing to try to evaluate, but you can imagine that this is really just counting something like 1 most of the time. So maybe there should be an asymptotic formula for this on the order of some constant c times z. Okay? And you can think about what this constant c should be, right? And maybe try to evaluate this. So maybe this should be some kind of an extended exercise to try to figure out what the asymptotic formula for a sum like this should be and how you should go about thinking about this, right? So let me say a couple of words and then you can continue this discussion maybe in the problem sessions. Whenever you want to, so you might want to evaluate this, then you might want to evaluate the asymptotic formula for L and so on, right? So in all these cases, a good way to proceed, there are a couple of ways you could proceed. One is to try to use an analytic method, like in our proof of the prime number theorem, to reduce everything to a problem of calculating residues. That's a very useful and robust method. Another way to think about it is that you can proceed in stages, starting with things that you know. So you know how to understand sums like counting 1 for the integers up to x, right? That's a pretty easy thing. So then from this, you can proceed to the next stage that you can then try to understand functions that are kind of like 1. Like, for example, the counting function of the square-free numbers. It's usually like 1 on the primes, except on the prime squares, you have to tweak it. So what I mean by this is that you can try to go from understanding how to compute the average of 1 to understanding how to compute functions f that arise as the convolution of a function 1 and a function g which is small most of the time. So here what does small mean? Small means that maybe g is some multiplicative function which is supported only on numbers which are square full. Maybe it's 0 on the primes, but then it's something else on the prime squares and the prime cubes and so on. So for example, if this is the indicator function of square-free numbers, then the corresponding g would be 0 on the primes, but it would be -1 on the prime squares, -1 on the prime cubes, and so on. And there are very few prime squares, prime cubes, and so on, so you can pretend that this is something small. Does this make sense? Right? So again, this is something to think through. So knowing how we can count the number of integers up to x, and if the g is suitably small, you can then count asymptotics for functions like f, and that would be one of these cases. This would be a function which is kind of like 1, except on the prime squares, prime cubes, you have to tweak it a bit. Okay? And then once you know this, you can kind of keep playing the same game. So once you understand how to count this, you can then try to understand how to count the function that you get by convolving 1 with itself, which is the divisor function. So I think you might have discussed this in one of the problem sessions yesterday to count. I guess you were discussing the maximum size of the divisor function, but you can also think about the average size of the divisor function when you average over all numbers up to x. Try to find its asymptotic. Once you know this, then this function is 2 on the primes and then 3 on the prime squares, 4 on the prime cubes, etc. But then once you know this, you can try to find a function which is usually 2 on the primes, but maybe differs on the prime squares by something. You can convolve the divisor function with some other function g that is small and try to find asymptotics for that. Okay? And you can proceed in the same way. You can go from this to D3, D4, etc., and find asymptotics for all of these. And more exercises, which again you can think about, is what happens if you have to understand things like d pi of n, which you wouldn't get immediately from this kind of reasoning, right? You can't somehow subtract enough integers to get d pi of n to be something that's small on all the primes. Okay? So you would need to think of a different method there, and the analytic method would be more powerful for things like that. So by d pi of n, I mean, what do I mean? I mean that you take zeta of s, raise it to the power pi, expand it as a Dirichlet series, and then see what those coefficients are. Okay, and what the asymptotics for that. Okay, so this is kind of a standard set of techniques for computing mean values of some simple multiplicative functions. If you use that, or if you just think through in this case what this size should be, you'll be able to prove that this guy behaves roughly like z, and so that means that our second term there is roughly on the order of, so our second error term, although here I've written everything explicitly, so I'll just put error term in quotes. That's a bit like it's on the scale of z squared divided by L squared, right? Which tells me that I can take z to be like square root of y, and this would be small. Okay, so the second term would be less than y over L squared if I take z to be y over L, or z to be square root of y. Okay, so that's so much for the remainder term. And what about the main term? So I have to still understand the sum over r up to z, and again with maybe it's this condition that p divides r implies p is less than capital R. Phi of R. Right? Now let me make a first simplification. Let's assume that first R is like z or bigger than z, so that I can forget about this condition. Okay? If I'm interested in actually counting primes, getting my upper bound for primes, I could take capital R to be z. There's no problem with doing that. So in this case, I want to evaluate this sum R up to z mu of R squared over phi of R. And again, the way you should think of this is that this function, the one supported on the square free numbers, is kind of like 1, right? Differs from 1 only on prime squares, prime cubes, etc. This is another multiplicative function. As we said, phi of R is roughly like R. So this should be kind of like the sum 1 over R goes up to z, which is like log z. Okay? And you can, in fact, have a very precise asymptotic formula for this. So once again, either by thinking of this function, trying to convolve with some suitable combination of 1, so that you can compare this sum with that sum. Okay? Either by doing that, or by writing down the analytic method and trying to compute a residue. In either way, you should be able to then prove that this is asymptotic to, well, you might expect that there might be some constant here times log z, right? But the constant actually happens to be exactly 1. So this is actually asymptotic to log z. Okay, so I'm going to leave this also as an exercise for you to discuss. Actually, this was on the list of exercises that Zeb and Benny gave out yesterday. Problem 9? 8? 9? Number 9, okay. Okay? Is this at least morally clear why this should be on the scale of log z? If you don't believe the constant, that's okay for the moment. Yeah? Yeah? The constant is 1?
Yeah. Is there any way to see that?
Well, okay. You have to do a calculation to see it, right? Okay. So another way you could see it is that, let's see. So this is mu of, let's think of what is mu of p squared over p minus 1, right? Yeah? Well, that is also the same as 1 over p plus 1 over p squared plus 1 over p cubed and so on, right? Which is like what I would get if I had 1 over p, 1 over n, if you like. Does that make sense? So you can see that, in fact, this sum, based on this explanation that I gave, you can see that this is actually bounded below by the sum over r up to z, 1 over r. Right? Okay, so there you can see the constant is 1. Yeah? But in general, this one works out nicely. Some other things work out nicely. But in general, there's no reason why something that you're computing has to always work out nicely. But in any case, this kind of convolution thing will work even when the answer is not nice, or the analytic method will work when the answer is not nice. You just have to do the calculation, and it's not very hard. Okay? So I could have just shown you this, but then, I want to make the point that you can calculate it anyway, in a routine way, not without too much thought. Okay. So that means that, let's say so to summarize, if I chose R to be like Z, then I would be getting that the number of primes in x plus y, in x to x plus y, is now bounded by y over log z. So now I'm going to make this, not an honest upper bound, but just an asymptotic upper bound. Okay? But if you work it all out, then it will actually be quite nice. It will finally be true with this constant 2, plus some error which is like z squared over log z squared. Okay, let me just put a big O here. And so choosing, as I said, z to be like square root of y, we get that this is bounded by 2y over log y, which was the Bruntischmar's theorem that we started out with. This good? So now some more exercises for you. Prove in the same way the analog that I stated for primes in a progression that's A mod Q. Right? So we said that here this was bounded by 2 times x over phi of Q log of x over Q. Okay? So you should think to yourself, what is it that we used in Selberg sieve? What changes do you need to make? You would again put this kind of Selberg sieve weight. So d divides n lambda d squared, right? Yeah, that's the thing that's going to majorize your primes. And then instead of summing over all n in an interval from x to x plus y, which is what we did here, you would be summing here over the integers n up to x with n congruent to A mod Q. right? But that's no big deal. Expand the square, interchange the sums. Then what's the problem that you have? It would be how many integers are there up to x in an arithmetic progression mod q, with n being a multiple of the LCM of d1 and d2, right? So that's the bottom line that you have to count. Right? Maybe you should begin by assuming that d1 and d2 are co-prime to q, so that there's no interference between d1, d2 dividing n and then being co-prime to q as well. Okay? But apart from that, this is easy. This is just a congruence condition mod q times d1 times d2, LCM of d1, d2. So you can say that this is again equal to x divided by q d1, d2 plus an error of at most 1. Right? So previously we counted how many integers there were in an interval that were multiples of a given number. Now we just have a very similar problem. How many numbers are there in a progression mod q that are multiples of a given number? And again, that's easy enough to count with an error of 1. Okay? Apart from that, everything else remains the same. So you would get a main term which should be of the scale of x over phi q, another term on the scale of z squared. So that kind of tells you how big you should choose z. So you tell me, how big should I choose z in this? The TAs have to answer, really? Sorry?
Wouldn't we want square root x over 2 to get a 2 on top?
Yeah, so it's just, you will again get z squared. Forget, just look at the structure of the error term. It will be kind of like z squared. The main term will change. Instead of having a y, which was the length of the interval that you had before, now you'd be the number of terms in your progression in a given progression a mod q. That's about x over q terms. So instead of y, you would have x over q. So therefore, z squared should be chosen smaller than x over q. So z is like square root of x over q. And then the rest of the proof goes the same way. Okay? So that's something to think through. Then the next thing for you to think through is that you can use this not just for counting the number of primes, which, once you understand the prime number theorem and once you understand primes and progressions, well, this doesn't look so exciting. But as I said, it's still exciting because it tells you what happens in any short interval or even for moduli q that are very close to x, which we don't know how to do by any analytic method. But anyway, here's something that's genuinely different. You can also try to count the number of integers n up to x for which n and n plus 2 are prime. Right? Of course, we would like very much to be able to get an asymptotic formula for this, or a lower bound for this that goes to infinity as x goes to infinity, which we don't know how to do. But this Selberg sieve would give you that this is bounded by 8 times the conjectured amount, which Dimitris mentioned last time. So some constant sigma S0 of 2 times x over log x squared. Okay. So if for counting primes we were off by a factor of 2, for counting, say, twin primes, we are off in a simple version of Selberg sieve by this factor of 8. Okay. Now, so how would you prove this? So don't worry about the constant 8. Try to prove it with any constant that you can get. Okay. So what would you do? You would have to now understand the sum over n up to x. Now I want to make sure that that n and n plus 2 are prime, which is to take here some quantity like d divides n times n plus 2 lambda d squared. Okay? Again, imagine the lambda d's are supported on numbers up to some point z, which is fairly small. So if n and n plus 2 are both prime, then I'll be only having one divisor that's being counted, namely lambda 1, and that'll be 1. So this will be an upper bound for twin primes. Okay? And then the question is, what kind of a quadratic form do you get? Well, you have to compute the same kind of object here. If you expand this out in terms of d1 and d2, then you would be led to understanding how many integers n are there up to x, such that the LCM of d1 and d2 divides n times n plus 2, 1. Okay? So let's just think very quickly about how you would solve this kind of a problem. Right? The best way to do it is to think of each prime that divides the LCM of d1, d2, and then to ask what condition this means. So if p is a prime that divides this, then I want p to divide n times n plus 2, which means that either n is a multiple of p or n is congruent to negative 2 mod p. Right? So if p divides d1, d2, then we want either n to be 0 mod p or n to be negative 2 mod p. Right? If p is 2, these are the same condition. You want n to be a multiple of 2. But for every prime p bigger than 2, these are two different residue classes that must be covered mod 2. Okay? And then you can use the Chinese remainder theorem to say what kind of progressions n must lie in mod the LCM of d1, d2. Okay? So the exercise here, you would then say, so n lies in some number of progressions. So question for you, of course, is what number of progressions? Right? And once you understand what this number is, so let's call this new d1, d2, say. And then you would be able to say that this, this quantity that we want is like new LCM d1, d2 divided by d1, d2 times x plus an error, which is, well, for each one of these progressions, you could be undercounting by at most 1. So the total number of progressions is this, so plus this number of progressions. Okay? And then you plug that all into Selberg's thing, and then see what bound you get. Okay? So far, so good? Okay, now let me make so, this is kind of genuinely a little bit more complicated than the example that we did, but if you think it through, then it's kind of, you will find it a very useful calculation to do, and James will do, extensions of this kind of calculation very much in his course. So. Now, one more point that's worth thinking through. So let's do. And this is kind of useful in various ways of formalizing the sieve. And I'll mention this a little bit more after we talk more about Bombieri-Vinogradov in the next few lectures. Is that in these cases, I kind of explicitly wrote down what this remainder term was. Say in counting in an interval or counting in a progression, it was just bounded by 1. And here also I can explicitly write down what this remainder term is. Okay? Maybe more generally, you might be counting something. We might be in some situation where, again, I'm counting over some n, doing something, okay, maybe in an interval progression, maybe over prime, having a prime itself in it or something, okay? And then I want to impose some condition like the LCM of d1, d2 divides something connected to that n. Doesn't not necessarily dividing n, but maybe dividing n times n plus 2, or n times n plus 2 times n plus 4, or n plus 6, or whatever. Okay? And then I might have the situation that I might have a main term depending on d1, d2, plus some kind of error term depending on d1, d2. Right? Is that okay? And the point to appreciate is that I'm not really worried about how big this error term is for every choice of d1, d2. For Selberg sieve to be used successfully, what I really want is that this average over d1, d2 up to z of some lambda d1, lambda d2 times this error term of d1, d2 should be controlled. Right? In other words, it could be that every once in a while there's some choice of d1, d2 for which I don't control this error term precisely, but if I can control them on average over all choices of d1 and d2, that's good enough for me. Okay? And usually in the applications, these lambda d1s and lambda d2s will not be very big. They will be bounded by, say, d1 and d2 to the epsilon, or they might even just be bounded by constants. Okay? So you really just need a bound for the error term on average. So by the way, when I say error term there, I'm forgetting anything about the sign of that error term. So imagine all that, what's being said there. Well, just to make it clear, let me put absolute values on this error term here as well. Okay. Now, okay, let me make one final point, which I think maybe somebody asked me yesterday as well. So in this choice of Selberg sieve, okay, I guess I have to wait for this to dry. So let me erase this other board so that we can wait for both of them to dry at the same time. So now, okay, I can say it while we wait for this thing to dry. So last time we had this change of variable going from the lambdas to the x's, and I told you how to choose the x's, right? And the x's were chosen to be essentially like the Möbius function, right? The Möbius function times L over phi L or something like that. Yeah? So then we plugged that into the formula for lambda, and we had a formula for the lambda d's, right? Yeah. So can someone recall what that formula is? Somebody must have taken notes. sorry, mu d, mu dr, right? Is that right?
It's mu d c dr.
Okay. And then c dr, we need to figure out what that is, right? I think that's, yeah, so d goes up to what? To z over r, something like that, right? Yeah. And then there was this other condition, if I have this capital R, that P divides D implies P is less than R, right? Let's forget about this if I take capital R to be like Z. Okay, can you tell me what this last thing was? No? Divided by phi of dr. Is that right? Times what? Times r. Okay. This is it? This looks right. Yeah. And maybe this whole thing is going to be divided by L, right? Yeah. Okay. So which was this sum of mu of r squared over phi of r, right? So you see, you can also try to evaluate this, because what is this guy here? Well, firstly, r must be square free, otherwise this is going to be 0, right? Because there's a mu r throughout here. Now, assume that r is square free, then d must be a number that's co-prime to r. Okay, otherwise this will be 0. So it's something like, so there's a mu of r that factors out. That's the Möbius function in r. And then what I get here will be a sum over d up to z over r. I can assume that d is co-prime to r. And then something like mu of d squared. If d is co-prime to r, then this thing just factors out. There'll be an r over phi of r that comes out, right? Phi of dr will be the same as phi of d times phi of r, if d is co-prime to r, divided by phi of d. And then this thing is divided by L. Is that okay? So you should think of it as like basically mu of r times some object. This r over phi of r, usually it's like 1. Okay? And then I have here a sum of mu of d squared over phi of d, which is kind of exactly like this sum mu of r squared over phi of r, except that instead of going up to r going up to z, this d goes up to z over r. Is that okay? And I drop this condition, just as I drop the condition there. Okay? So yet another exercise is, at least when capital R is chosen to be z, is to get an idea of what the optimal answer in Selberg sieve comes out to be. And the answer is that lambda r is approximately like the Möbius function of r times this guy kind of behaves like log of z over r, because d goes up to z over r now instead of just z, and then divided by this L, which has a log z in it. Okay? So in other words, the point is that the optimal choice in Selberg sieve kind of looks like what you might have suspected when you started doing the combinatorics of inclusion-exclusion. We had a sieve with the Möbius function in it. The optimal choice in Selberg sieve is not so different. It still has the same Möbius function in it, just smoothed a little bit to have so this is some weight that starts off being at 1 when r is small, and then tapers off to 0 as r goes to z. And then it's 0 from z onwards in our assumption. Okay? So another way to say what I've said here is that suppose I knew this to start off, after I do the calculation, I know what the optimal choice for lambda r's is, namely something like this. So I could have started out my whole calculation with just this situation in mind, and then tried to evaluate everything for that choice. Okay? If I can do that, I might also be confident that I haven't lost a whole lot in restricting myself to this situation, and I would get more or less the right answer. Okay? So sometimes that can be useful. So I think James, when he describes his calculation, will do it in two ways, I think. One by diagonalizing, and the other is by knowing what the optimum answer is going to be, and then just trying to evaluate the optimum answer to start with. Something like the optimum answer. Okay, so now I need to give a few more exercises. So we haven't used this capital R parameter so far, right? So now let's think a little bit about capital R and what it buys us. So what this capital R allows me to do is actually, I'm not just counting the number of primes in an interval, I'm really able to count the number of integers between x and x plus y, all the prime factors of n being bigger than r, right? I've sieved out all the prime factors up to capital R. Okay? So of course there's no, if r happens to be bigger than z, there's nothing I can do about it. But let's say if r is fairly small, so let's imagine that we are in this kind of situation. Think of r is like y to the 1 over 100, right? So remember that z was chosen to be y to the 1/2. So we are now, let's say we are thinking of the situation where r is substantially smaller than z. Yeah? So you might think, well, in this case, I'm not asking for a whole lot. I'm not really asking for primes. I'm only asking that these numbers should not be divisible by a small prime factor. Okay? So you might think that I should be able to get some result that's better than this upper bound of twice y over log, log z or whatever, to try to get an asymptotic formula for this. Is this approximately the same as what we should guess, which is y times the product over p up to r, 1 minus 1 over p. Right? To not be divisible by any prime up to r, the chance of not being divisible by a given prime should be this 1 minus 1 over p, and they should all be roughly independent of each other, at least if r is not too big. Okay? We already saw that if r is very big, then this is not true. This was this 2e to the minus gamma is not the same as 1 calculation that we did last time. Okay, so how would you be able to make a statement like that? Also keep in mind that everything I spoke about in Selberg sieve is really giving you an upper bound, right, and not a lower bound. Okay, so firstly, let's see that we can actually get an upper bound which is kind of very, very close to this, and let me then say how you can kind of leverage the upper bound to get also a lower bound of the same strength. All right, so there are two things I want to explain. So first, let me explain. So of course, I'm not going to explain it. I'm going to make you do the work. So let's think of the bound that we had in this case would be a sum over r up to z. P divides r implies p is less than capital R. Mu of r squared over phi of r. Right? And again, for concreteness, think of the situation z is like square root of y, and capital R is a small power of z, y to the 1 over 100 or z to the 1 over 50. Okay? So if you kind of believe this thing that I said there, this is kind of like trying to think about the sum over n up to z, 1 over n, forgetting the square free condition and forgetting this phi of r. but only summing over those n, all of whose prime factors are less than r. Okay? Now you can kind of see that if z is really infinity, no dependence on this, and if I just had to sum this, that would just give me the inverse of this product. Right? So that's a good sign. So just as if you fix r and let z go to infinity, it converges to the product that I want. So let me actually write it here. Z goes to infinity for fixed r. This goes to right? And then the question is, well, if z is r to the 100, then what does this sum go to? Okay? So there's a let's see. Maybe I should not chance this. So now I said to count things like this without this condition, you can think of this problem as just counting the number of integers up to x, and then you use partial summation, and then you get the log, right? So if I now want to put in this condition that all the prime factors of n are small, then you might want to start by trying to understand something about the sum over, about the number of integers n up to z, such that all the prime factors of n are at most r. Maybe it's the chalk that's wet rather than the board. So let's see. Okay. So let me say one thing here. So the set of numbers, all of whose prime factors are smaller than r, this is called an R smooth number. Or since Emmanuel is here, I should call it, the French call it also a friable number, or friable. And friable means crumbly. It's an actual English word. So a smooth number is like a crumbly number. It crumbles into lots of small prime factors. Okay? So these numbers are extremely useful all over number theory. They're also useful in cryptography, or if you want to have factoring algorithms, a lot of them depend upon smooth numbers. Why are they important? They have two very nice properties. Because all their prime factors are small, it's relatively fast to try to factor a given such number. Okay? Another way in which they are useful is that in theoretical applications, for example, to Baring's problem, but also for this summer school, Zhang's theorem, which Emmanuel will speak about a bit more, also uses these smooth numbers very crucially in extending this Bombieri-Vinogradov theorem that we haven't discussed yet. And the advantage that they have is that a smooth number has divisors of essentially any size that you like. Right? I mean, a prime number doesn't have that. It has only two divisors, one big, one small. Or if you have a product of two primes, you don't have so many options either. But if you have a really smooth number, then you can go in a greedy way. Just throw in some prime factor, throw in the next prime factor, If you want to pick a divisor of some size y, keep throwing prime factors until you just cross y, and then stop. If all the prime factors are less than r, you would not have crossed y by more than a factor of r. So you can find always a divisor between y and yr for any y. That turns out to be an extremely useful property. This way of being able to factor a number into any size that you want is a very useful property. And that makes these numbers very, very valuable theoretically. And for, say, practical cryptographic things, like I said, if you have to factor the number, you only have to check its prime factors up to r. And then you would get its complete factorization. Okay, so these are very useful numbers. And what you would like to know is that there's a plentiful supply of them. So if you put z is r to the u, then the number of, so this number is denoted by psi r to the u r. So the number of integers up to r to the u, all of whose prime factors are less than r. And there's an asymptotic formula for this, that this is asymptotic to a function rho of u times r. Okay, at least if u is not too big, you can prove this asymptotic formula, where rho is an interesting function. It's the Dickmann function times r to the u, thanks, right, times the number of integers up to r to the u. It's the Dickmann function, which is defined like this. It's 1 if u is less than or equal to 1. If you're counting the numbers up to r, all of whose prime factors are less than r, that's easy. This rho of u should be equal to 1. And then after 1, it's given by a differential difference equation. So u times the derivative of rho is the value of the function rho at u minus 1. Okay? So this tells you then what to do between 1 and 2, and then 2 and 3, etc. So between 1 and 2, and then you can keep integrating to figure out what it is between 2 and 3, 3 and 4, and so on. Okay. Do I have 5 more minutes, Emmanuel, or when do we? Yeah. Okay. So by the way, this function was also considered by Ramanujan about 10 years before Dickmann. In his unpublished notebook, he has kind of one page where he writes down this function for u between 1 and 6. And he writes down various iterated integrals and says, and so on. But what he doesn't notice, I think, is this differential difference equation. So that's not in Ramanujan, but the formula for rho of u is there for several values. Okay, so once you know that, you can now use partial summation with this Dickmann function to evaluate this kind of integral. Okay, so there's a couple of things that you have to work out. So now, and one more fact that you need to know. So let me just say as a fact to think through. From these relations, you can prove that this Dickmann function rho decreases extremely rapidly. It kind of decreases like 1 over u factorial. So like u to the minus u. Okay? So it decreases extremely fast, but still it is a constant times, times r to the u. So if you use that in partial summation, so again, this is an exercise. to discuss with Zeb and Benny. So from this, you can compute that if I take the sum over n up to r to the u, p divides n implies p is less than r, 1 over n. You can prove that this converges to this product that you expect, p up to r 1 minus 1 over p inverse. This would be what you get if u is like infinity, right? It becomes the whole sum. But it converges to this extremely rapidly. It's this plus something like u to the minus u. Okay? In other words, the point I'm trying to make is that the tail of it, the terms with r, with n bigger than r to the u, because this Dickmann function decreases so rapidly, they give you only something on the scale of u to the minus u times the full sum. Okay? So that means that if I now go back to the Selberg sieve, if I return to the situation that I had there, z is like y to the half, if r is like y to the 1 over 100, or z to the 1 over 50, right? And if I know this, then I know that the sum over r up to z, all the prime factors of r being small, that this is kind of like the expected product times, well, u for me is 50, z is r to the 50, so something like 50 to the minus 50. Right? So this is, of course, a meaningless statement, but you know what I'm trying to say. Okay? So in other words, this Selberg sieve gives you an answer now where you're not losing this factor of 2, but you get to within 50 to the minus 50 of the right answer. Okay? As an upper bound. Right? Why is that good enough? I've just told you how to get an upper bound, right? How do you get a lower bound, which is also off by just a 50 to the minus 50, let's say. Okay? So how to get the lower bound? I'll say 2 words about this and then we'll stop. Well, this is not too bad. So suppose I want to count the number of integers between x and x plus y. P divides n implies p is bigger than r, right? This guy. I will just do some kind of inclusion-exclusion. This will be all the numbers up to y minus the numbers that I have to exclude. Okay? Now, what are the numbers that I have to exclude? They are the numbers that have a prime factor which is less than r. Okay? So let me pick the smallest prime factor that this number has. So it will be a sum over primes p that are less than r, right? And then I will be counting, so n must be a multiple of p. There will be the number of integers n between x over p and x plus y over p, right? Such that all the prime factors, let's call them now L, of n are bigger than p. Right? Is this good? I've just counted it with the smallest prime factor that it contains. Okay? But now I know how to get an upper bound for this. That's just what we discussed, the upper bound here. It's actually a very good upper bound, exactly the right upper bound, with a small error missing. So I put in the upper bound here. It's with a minus sign. So the upper bound that I put in now gives me a corresponding lower bound for the quantity that I want as well. Right? So now So the sieve upper bound now gives a lower bound, right? And then this lower bound is good enough to give an asymptotic formula with an error of this 50 to the minus 50. So in other words, I'll be able to get a lower bound of 1 minus some constant times 50 to the minus 50. That's the answer. Okay, so one more question. Why can't I do this in general? I had an upper bound for twin primes, so I carry this out, do this kind of going from upper bound to lower bound step, right? Put in my upper bound for whatever I have, and get a corresponding lower bound, right? And then we are done because we'd have shown there are infinitely many twin primes. The only problem is that the lower bound that you get could be negative, okay? And it may not give you much at all. So what happens in the sieve is that the sieve, as an abstract principle, works always to give upper bounds. You can sometimes use those upper bounds to get lower bounds as well, but oftentimes in the situations that you really care about, your lower bound might be negative, and you may not get anything meaningful out of it. And then there's a big theory which tells you in what kind of situations you will get a positive lower bound. What do you need to know about your sequence that will enable you to get a positive lower bound? Okay? But this is some kind of introduction. So next time I'll say more about a different kind of sieve called a large sieve, and we'll use that to say more about primes and progressions, which is the Bombieri-Vinogradov theorem. Okay, thanks.
Okay, so I guess we just take a 5-minute break and then, well, unless there are questions.
Questions, yeah.
For sound.
We can also ask during lunch.